welcome to Ladyada.
Hey everybody, and happy Pride weekend to all y'all here in New York. It is colorful out. We went out earlier and now we're home working on electronics. So let's get right to it. Mr. Ladyada, do we have any updates for?
We have some Raspberry Pi folks visiting, so we'll have some photos and if there's any interesting things we can share, we will. And then a full week of shows and more leading up till July 4th, 5th. Keep an eye on the website. We have our shipping dates and more. And happy American birthday soon. So let's kick it off, Lydia. What is on your desk this week?
Okay, so this week, well, I've been working on the toy hacker the most, and we actually got like prototype PCBs Wednesday morning, and so we like rushed to get a demo working for Wednesday, and then we also did some super funny little videos starring baby Ada. But I thought let's go to the overhead and you can show off where we're at with this project. Okay, cool. We'll zoom out a little bit and I'm maybe tuck this cable away. So as previously shown on this desk, hacking and modding this really common toy that a lot of kids get. It's like, literally $10, free shipping. And it normally plays like classical musical tunes. It's like Baby Einstein brand. So it's like, we will make your child smart, whatever. But wouldn't it be cool if your child could be goth or, listen to Taylor Swift? So we've, we took apart this toy and we, kind of analyzed the circuit, and it's got like simple LEDs and this epoxy blob. And there's like no real way to reprogram it. This is, designed to be, again, it has to be $10 with free shipping. So this is meant to be as inexpensive as possible. It's not modifiable, but we want to change what the music is because I really like this enclosure. It's great. It can run on like 2 rechargeable batteries. It's got this nice case. Obviously I took the battery cover out, but normally it has screws, so it's really easy to assemble and disassemble. So we've updated it. The board's inside. Well, I'll show the board in a moment.
Oh, yeah, and I have a little video.
Oh, why don't you show the video and then
Okay.
I'll go back to this.
Okay. And there's the board.
Yeah.
Okay.
Okay. So we're back. So yeah. So when I press the button, when I turn it on, you can actually see the little yellow NeoPixel here. That's it's running CircuitPython right now. I don't know. I mean, I might eventually like port it to Arduino, but CircuitPython has really good audio playback and everything. And then, you can play music. And then what I did was, I just wrote some simple code that every time you press it, it plays and then pauses the audio mixer, which is running in CircuitPython. So let's first turn it off, so I don't accidentally. I have to be careful. I can't have it more than like 4 seconds, or YouTube is like, hey,
Yeah.
you're trying to pretend to be Taylor Swift.
It'll be okay.
You can play any length music,
It'll
but I don't want to risk it because the other video did get demonetized, right? Already, we cannot
within milliseconds.
within like 2 milliseconds. Okay, so opening this up, I'll show the board as it's installed. And Mr. Lady, maybe you can give me like a note when I get to 15 minutes so I can keep us on track.
Here, 5 minutes.
Yeah, okay. So okay, I'll open this carefully. Okay, so this is the top and this is the button. That's the top case. And then this is this little plastic piece that's translucent. So normally it has a couple LEDs. I got more NeoPixels. And you can see I ended up doing a lot of blue wire hacking. In this case, I use purple wire. But I use wire wrap wire to redo a lot of the power supply. So, the power supply was something that I kind of rushed through a little bit because I just wanted to I was more interested in testing for the first version, like, is the outline correct? Did I wire up the ESP properly? The micro SD and boost converter, like, did I get that all working? And I wasn't like as careful about the power supply because I kind of wanted to get those PCBs on order. So a lot of cut traces and stuff got rerouted here, and I'll show what I did on the schematic because I'm going to go into more technical detail. But ESP32S2 module, and I kept the same PCB outline, but I noted that in the PCB there was like clearance here, so I could have the antenna stick out, which is kind of nice. It means you get good antenna range. The boost converter works totally great and fine. I soldered this to the battery pad, so this comes, the battery case kind of sticks through and then gets soldered directly to the PCB. The elastomer button fit perfectly nicely on top of there, and then the speaker that comes with this got soldered in, and it comes from behind here into this I2S amp. The USB Type-C works fine. Maybe I'll plug it in so we can see it on the, I think it, maybe, oh no, I do have to turn it on. Sorry, it's been a while. Let me see if it shows up. Oh, so also this cable might not be plugged in. Oh, my USB hub's off. That's why. So I was like, why isn't it working? You have to turn it on. That's why. Okay, so now, okay, so you see, so this is the reset button. So if I press this, it will restart CircuitPython. So yeah, let's go to the computer, and I'll show, although I think I just erased it by accident. Oh no, I did. That's funny. Okay, so let me, I do have the code again though, so let me grab it. It is under dev boards. Here you go. Oops. That's odd. It should be. No, I think I might. Oh, you know what? This is the other board. I think I messed up with this one, but let me open up the terminal. There you go. So just here I've got CircuitPython. I got a build made. Dan Halber just compiled a quick build for me. I will say that playing with the ESP32S2 with I'm also using it with Wi-Fi workflow and with I2S and the mixer and NeoPixels. I did get like a lot more flakiness than I wanted. So I'm going to get a debug build and look at the debug output to see what's possibly going on, because I was getting a lot of hard faults. And as I will admit, I was pushing it kind of hard. I was like doing all this, like it's doing NeoPixels and it's doing audio and it's like looking for key matrix button presses. So let's just drag code.py over, and then why is this? There's a way to erase, let's see, import storage. Let me erase the file system. Start clean, because I think I corrupted it. Okay. Oh yeah, weird. Why did it come up this time? Okay, anyways. All right, so here I've got the, no, that is, oh, I see, it recreates settings.toml. Sorry. Large icons. Okay, so let me drag this over. And the library, and then I will open the code.py. Okay. And this is visible. All right, so yeah, so I'm using a lot in this demo. The thing that is, I think, particularly taking up a lot of my processor time is because it's digital I2S audio, and I'm still kind of figuring out what like audio levels I want and the gain, and like I don't want to overburden the speaker because the speaker takes up the most power. Is I have I2S out, but then I'm putting it through a mixer, and then I'm using the mixer to set the digital volume level. Yeah, go ahead. Okay. Adam loves to crash. That's okay. We're going to use XEmax. Doesn't crash. Never has, never will. Okay. So I've got the audio mixer where I set the volume to 50%. And, I probably won't do this in the end because it is like, again, very, I want to say like energy consuming, but it's like processor consuming to have it apply a gain to every sample going through I2S. So what I'll probably do is I'll figure out like the gain setting I want on the amplifier, and then I'll just be like, hey folks, you can put it through the mixer, but if you just in Audacity set your volume level to be, whatever, 70% of max, it'll sound good through the speaker. I'm using, there's two switches technically. I've got the button, which is the onboard, boot button, and I've got the card detect. And I use the card detect to determine, see if Adam will start properly this time. When I insert an SD card, so let me find, I think this is a good SD card. I insert SD card into the onboard slot. Yeah, it detects it and it's like, okay, cool. I found an audio file. And now if it move my head, you can see it's like, oh, there's one audio file on the SD card and one on the onboard storage. The onboard storage isn't big. And then when I hit the button, it says, let's do a slide. I can, it uses key events and doesn't actually look for, it doesn't like test the digital signal. It actually uses this like interrupt, like background interrupt based way of monitoring the key presses. Reason being is I want to eventually have this be a very like ultra low power setup where it goes into deep sleep mode while paused, because most of these toys I've noticed, to their credit, you don't actually have to turn them off. Like you turn them off if you don't want to accidentally turn them on. But for battery usage, they consume almost no power when not doing something. They're meant to sort of stay on and like be accidentally left in the PlayStation area, crib, whatever. And then whenever the button is pressed, that's when power gets consumed. So I kind of started this with the idea of that, okay, I'm going to be doing deep sleeps and I'll use the button as a wake up, and maybe the SD, also as a wake up signal, not as a something that I'm polling for. And then after it's done playing one audio file, it goes to the next one. This one. So far so good. For audio size restriction, I'm kind of going with 22 kilohertz, 16 bits per sample, but you can do like 44 kilohertz if you wanted to, although the speaker quality isn't that great. And then yeah, there's not actually a lot going on, to be honest. It's pretty straightforward. It's just using the button and it's just like it's scanning for WAV files. One thing that is interesting is as I was writing this code, I was like, oh, how do you like I couldn't remember like iterating through a directory and getting like the WAV files. And so I ended up going to what was it? Open AI. We can find my chat. And oh no, I didn't have my chat. Oh, there it is. I was like, oh, can you just write a CircuitPython sketch that plays WAV files through iTwist, looping through each file on the SD card? And what's kind of cool is, so I've written this code. Like if I really wanted to, I could sit down and write it. Like I've written it and it's in one of the guides, but we have like 3,000 guides, and I couldn't easily remember which guide was it that had this. And like the search is always like not, it'll find anything that has WAV, anything that has SD cards. And what's interesting is I actually did a pretty good job. Like I didn't end up using the exact code, but I did like pull out little pieces after verifying that they're correct. Like I don't trust the code generated from ChatGPT, but it is like a good way to like search the corpus of CircuitPython code that has been already written and just get me the example that I'm looking for. I think, Mr. Ladyada, you've done sort of similar stuff
Yeah,
with,
just my gripe about um, people. Uh, it's like four people.
yeah.
Every time we do anything that has ChatGPT or OpenAI involved, they're like, "You're stealing from Herp Derp Derps." So this is a lot of times we're looking for our own code. Like
Yeah.
we put open source code out there, and we're using a tool for Lemore to find your own code.
Actually, I think this is Katnie's code. I'll tell you why I think it's Katnie. This is interesting. It's
Yeah,
like,
well,
it,
Adafruit. Yeah, just by
yeah,
the way.
because this thing finally it mounts the SD card. That's a very like Katnieism. Like
Yeah,
at the end of that paragraph, she's like, finally, da 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 da.
yeah.
Like it's how she writes
So
documentation. So I think this is something that Katnie originally wrote.
I don't know who's going to be listening to this, and um, we'll see examples, but um, we just get singled out. But we're the ones who put out the most open source code, so
Yeah, this is my code.
shouldn't we be able to use this tool to look for our own code?
Yeah.
I use Google to find old articles I wrote. It's just bonkers. Anyways,
See, it's not. I think it's actually. I wasn't going to mention, but it's like then I realized. Oh yeah, I should mention. Like it's it's a good resource as one of your many tools in your toolbox as writing code. Like it definitely saved me from typing a lot because I would have just like written it by hand based on the read the docs documentation. But I was like, oh, I bet like it just puts everything in the right order, and then I put it. Okay, so all right, let me just show the PCB. Anyway, so far CircuitPython code. I'll show the PCB and then we'll go to the great search. So the thing I made a mistake with the PCB, and maybe we can go to the overhead real fast because I'll show. Okay, so right, so we've got the AA batteries here, right, and this provides like 1.7, like maybe 1.8 volt at the very lowest. We can get to 0.9 volts up to about like 3.3, 3.4 if the batteries are fully charged. And then these go through a boost converter here and they get boosted up to 3.3 volts. And then normally here, this is 5 volts in from USB, and then this gets regulated to 3.3 volts here. And what I did is, like, again, I was kind of in a rush. I was like, well, I'll just tie the outputs together and I'll deal with the consequences later. So let's go to the computer and I'll show the consequences. So this is what I originally did. I have, again, this boost converter. The battery, yes, the battery comes in to V in and gets boosted to 3.3 volts. And here's like the feedback. And then what I did was, oh, I'll know what I'll make it so that when V bus is high, when the 5 volts is plugged into USB, this pulls up, which means this pin N goes low, which means that this gets disabled. So the boost converter is disabled when VUSB is plugged in, and then it'll like change over to the VUSB regulator, which would be an LDO. And it just totally didn't work. It would have worked if everything was like perfect and idealized, but the reason it didn't work is I thought like, okay, well, this feeds out to 3.3 volts, but then this is, disabled, only one regulator is running at a time. But what actually happened is that when this is boosted and giving you 3.3 volts output here, the 3.3 volt leaks just a little bit back here, like a tiny, tiny little amount, like a milliamp or whatever, through whatever pass transistor, diode, whatever. It leaks back here, pulls the V bus high again, very, very weakly, but it does pull it high just enough that this, sorry, it pulls it, yeah, it pulls it up so that this never gets disabled when the battery turns on. So like if you plug it in, you turn on the battery, you'd hope that this would pull up high, but what ends up happening is it pulls up just enough so that this gets turned off, and then it like it would oscillate up and down. I don't think it oscillated, but it's basically like it didn't work because of the slight leakage current that came in from the 3.3 volt back into the V bus. So the battery wouldn't work. It would only work under USB. So The solution is, because I didn't want to have to like pick a regulator that I knew didn't have, because there are regulators that have like true disconnection between the two, but I didn't want to get one of those. So instead, I redesigned it. And I didn't do like kind of what you're supposed to do. I did something also slightly bad, but probably better. Okay. Is VBAT, which is again like 2 to 3.3 volts or whatever. I boost up to 3.8 volts. And I boost up to 3.8 volts because then I can have it go through this power selection circuit that's like copied from every feather pretty much I've done the last couple of years, where it basically does an or, like, you know, whichever is, if VBus is enabled, it will go through VBus will power this. It'll disable this pass switch, but if you have if the USB port isn't connected, the battery will go through this body diode, go into V high, and then this will pull low to turn it on even harder. So this ends up being like kind of an ideal diode, a very low RDS on diode. And then it's 3.8 volts so that there's a little bit of voltage drop over this 3.3 volt regulator. You know, you have a little bit of drop in it, even though it's an LD, a very, very low dropout LDO. And then you get a nice clean 3.3 volts out. And that was what powered the circuit. So it's a little bit of a hack because, you know, ideally we would have something that has, that can have the ideal diode into it and then have this, whatever this power supply regulator give you a clean 3.3 volt out. That would be either a single-ended power converter, like a SEPIC, or it would be a buck boost. But the thing is, I have these parts stocked. I don't have like a buck boost stock that's inexpensive. Like this regulator is very inexpensive, and I've got the TPS 61023 stocked, and it's very inexpensive. So even though this is not very, like, it's kind of weird to like boost it and then LDO it down, it does work. So we're gonna try it. So Rev B, I've ordered the PCBs. Basically, that's the only change I've made to the power supply, and when we get it back a couple weeks, we'll see how it goes. So on the topic of buck boosts, let's go into the Great Search.
Where in the world is that part I need? The Great Search with DigiKey.
A great search brought to you by DigiKey and Adafruit. Every single week, Lady uses our power of engineering to help you, yes, you find the things you need on digikey.com. What is the great search this week, Lady Ada?
Okay, this week, Great Search is a buck boost converter that will run off of either 2AA batteries or a 5 volt input. And you'd have like an ideal diode input into those. So assume that you have about 2 volts to 5 volts input and 3.3 volts output. Let's look at my schematic on the computer and I'll show what I'm replacing. Let me hide this part. Give me a little more space on the screen. So this is what I'm doing on this design, which is, it's a little unkosher, but bear with me. I have this board where VBAT is about 2 volts. It's 2 AA batteries, so it's 2 to 3 volts. And I want to get 3.3 volts out in the end, but I also have either AA batteries or 5 volts plugged in through USB. So this VBAT boosts up to 3.8 volts through this TPS 61023. And then it has a little, like an OR diode power selector here with VBus, which is USB 5 volts. And those go into an LDO to give me a clean 3.3 volt, which is fine. But it's a little bit like, boosting and bucking, whatever. If you want to have like an all-in-one solution, what you could do is get a buck boost converter, something that will take either the high voltage VBus 5.5 max, 5 volts, or as little as VBAT 2 volts, and give you somewhere in between, right? So it's like, usually you have a boost converter from a low to high, or a buck converter from a high to low. But what if you have input that could be either higher or lower? You want a buck boost converter, right? Which is like great marketing. It's like, is it a buck? Is it a boost? Dessert topping, floor wax, buck boost converter. So let's go to digikey.com and we'll find a buck boost converter. So let's search for buck boost. And we want a voltage regulator, not a controller. The controllers usually you have to connect external transistors and diodes, and you have to like it controls the regulator, the regulation circuit. We want something that's all in one. We're a little lazy. We kind of want we want like a bento box. It has a little bit of everything, and we don't have to think too much. Let's go with something that's active. We want one output. And the output we want is 3.3 volts. So we'll just say, hey, you know, it can be positive or positive only. We don't want a negative output. Often these DC converters can also invert the voltage for you, but we don't want that. And we want something that's normally stocking. And just for now, we're going to exclude marketplace. So just stuff that's stocked at DigiKey right now. We also want a synchronous rectifier. That means that we don't need an external diode. It usually means your performance is a little bit better because instead of, you know, if you've ever studied buck or boost converters, you know, there's two switches, right? You're switching through an inductor back and forth. And sometimes people replace one of those switches with a diode. Very inexpensive, works very well. But if you want a little bit more efficiency, and often the price isn't too different, and usually you get true power disconnection, a synchronous rectifier. I personally like synchronous rectifiers, but we all have our preferences. And then the input, the minimum input, remember we're going to have two AA batteries. AA batteries, when they get down to like their lowest level, it's about, you know, 0.9 volts. So you want something that can handle 1.8 volt input at a minimum. And the maximum 5.5 or 6, that's fine because we're, again, USB is 5.5 max. So let's apply. That really cut it down because we limited, we only want like a low voltage regulators. And there's a couple of really good options already. We're starting to see like a bunch of chips come in here and look at all these in stock components. Wow, isn't that wonderful? A real change to see so much in stock. One thing I don't want is anything with BGA because I'm kind of not a fan of BGAs. So I'm going to option click and I go through and because you can search for a filter, but you can't like reverse filter. So I'll go through and I'll deselect those. Okay, so now I've got 100 options, which is a really good thing to look at. Okay, so we've got a couple options sorting by price. Looks like you're going to pay like about $1. Not too surprising. TI is well, it's actually also, let's look also in stock only. All right, so we've got 56 options. Not surprisingly, Rich Tech, they make a lot of power supplies, regulators. TI has a lot. And you'll notice the TPS63 series, we actually stock a breakout board with the TPS 60. I think all their they have a line of buck boost converters called the TPS 63. 63060 is what we use here. This is a 5-volt buck boost from 3 to 12 volts. It gives you like 500 milliamps or an amp. So it's, yeah, these are nice chips. I've used this family before, so that's kind of good to know. There's a couple in this series. It looks like different current, you know, built-in current limiting. There's also Rohm. There's also a few that have different either adjustable or fixed outputs. So you see some of these are fixed, some of these are adjustable. Since 3.3 volts is really, really common, I'm going to just select 3.3 volt fixed output. Now I got down to like 10 options. Again, all these are going to be really good. I'm not going to say like the Renaissance one, TI is good. Because I've used TI before, I'm probably going to just look at this one first. The next thing you want to look at is this. I mean, you want to simulate this and make sure it's, of course, it's a good chip for you. And TI has a good simulator for all their chips. But you I have to kind of approximate how much current I'm going to need out of this thing. So I'm going to need about like at least 500 milliamps to drive that speaker. And the ESP32, especially if it's going into Wi-Fi mode. So like 500 milliamps is kind of like my thing. But remember that the 500 milliamps is not the switch current. The switch current has to be the max peak coming from inside the lowest voltage that could go in. So if you're at 1.8 volts, you're pretty much doubling. So I need at least 1 amp of switch current. And so these 800 and 900 are not, they're really at the limit. I don't think that they're going to necessarily be able to supply how much current I need. Because again, as the battery dies, I'll say it's going to be hard to get that much current out of a dead battery, but you know, you also have to give yourself some, give yourself like a 20-25% headroom for inefficiencies in the circuitry. So let's go with like a 1.6 plus current. It says output, but usually that's actually the switch current, not the current output, because on a buck boost, they're optimistic. And then some good options. So I actually kind of like this this TPS 61030. I mean, it's $1, which is a really good deal in quantity, and they have lots in stock. So this one is kind of nice. I mean, I've used this family. Look at the data sheet real fast. 1.8 to 5.5, up to 1.2 amp output in step down, 800 milliamps from 2.4 volts. So yeah, about 500 milliamps from 1.8 volts. Really low quiescent current, which is good. I want it to work like I've mentioned in the previous segment. This is going to mostly be on all the time and only playing audio when somebody presses a button. So the boost converter will kind of always be running. So quiescent current, a good quiescent current is important. And also really simple, easy to use schematic. I mean, some input bulk capacitance output, and then inductor. Notice you don't need a diode because it's synchronous, and you don't need to do feedback resistor divider either because it's a fixed 3.3 volt output. So this is my pick, the TPS 63001, a lovely buck boost converter.
That's a great search.
Where in the world is that part I need? The great search with DigiKey.
And that's our show for tonight. Thank you so much, everyone, for joining us. Special thanks to all Adafruit team members, everyone in the community, and the customers that help this thing go every single week. We'll see you during the week. That is this week's Desk of Ladyada.
Thanks, everybody. Have a great night.